This is Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm going to deal with the course Computational Dynamics. And today's topic we will see about grid independency, time independency, and the convergence of a numerical scheme. So first we will learn basically what is a grid and what is the importance of grid in the CFD and how it will play a major role in the numerical simulation. And then after we will see how the time independency study will play a major role in the numerical simulation we will see, and what is the convergence of numerical simulation we will see in detail. So here if we see a grid, so let me draw a 2D mesh. So here we have x and y z lines. So the intersection of the x and y grid lines so will form a grid point. So here, so basically these are called the grid points. So the 9 points are called grid points or node points, which are formed inside the domain. So therefore these are called the internal points. And here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 points which are on the boundary. So therefore they are called the boundary points. So let us see basically what is the meaning of grid independency study. So here let's say we have the grid points of totally 12 plus 9, which is of 21 grid points. Okay. So this set has 21 grid points. Now we are performing a simulation. So let's take flow over flat plate. So for the flow over flat plate, let us take this domain and we have 4 boundaries. So boundary BC1, next BC2, and next BC3, and next BC4. Let us take. So for the BC1, what we will take is like this as a wall. So for the wall, we will take it as no slip wall BC. Okay, so no slip wall BC we will be taking, and for the BC2, let us take this as a pressure outlet. Okay, and this is the boundary condition what we use, and the name of the boundary you can use outlet. So the name of the boundary is different and the boundary condition is different. So when we take the domain, so first we have to define basically what is the name of the different boundaries. And if we go back, so how do we construct the domain? So first we will take the key points or the coordinates which we need to construct the boundary. So how many coordinates we have? Let's take 1, 2, 3, 4. Okay, so let's do the reverse process. Let's construct the domain using first coordinates, and then we will construct the lines. After constructing the lines, we will create the domain. So let me take the point, this one as 0, 0. So this is the first point, and this one as 0, 1, 0. So this is the second point. So 1, 2, and the third point. So this would be 1, 1, and the fourth point. This would be 0, 1. Okay. So these are like this is the third point, and this is the fourth point. So we have the 4 coordinates. So by joining 2 coordinates, so we get a line. Okay. So how many lines do we get? So we have the 4 lines actually. So we have 4 lines. So for these 4 lines, so combination of these 4 lines will constitute a domain actually. So this is a single domain. So which is formed by combination of 4 coordinates 1, 2, 3, 4 and 4 edges. So basically for the 2D domain we call it as edges or the boundary domains. So there are other names. So let us call it as the 4 surfaces. So surface 1, surface 2, surface 3 and surface 4. So here you can take this as figure 1 and figure 2. Let us take. So the figure 1 basically shows the grid or the mesh which is dividing the figure 2, which is called a domain, into subdomains. So observe figure 1 and figure 2 carefully. So in the figure 2 there is nothing which is present inside the domain, so it's empty. So figure 1 if you take, so you have the grid points. So how do we create this mesh, we will see. First, we have 4 edges, 1, 2, 3, 4. So these edges are actually to be assigned points. So let us take edge 1. So for the edge 1, if we give, let's say, 4 grid points, 1, 2, 3, 4. So the parallel edges has to be given same number of grid points. Same 1, 2, 3, 4. So 4 grid points has to be given. So along x-axis, so if you are giving 4 grid points, you have to give same 4 grid points. Along y-axis, if you give 5, same you have to give 5. So you can give equal number of grid points along x, along y. So there is no rule and restriction of giving the number of grid points along particular axis actually. So the grid points, choice of the grid points is basically coming out of the physics of the fluid. So what you need to capture and what physics we need to see. So this is very, very important. So therefore, first initially when you perform a simulation, the major important thing is to govern what should be the minimum number of grid points to study the flow behavior of numerical simulation. Okay. So first let us see the generation of grid. So I have given 4 grid points along x direction. So let me give again same 4 number of 4 grid points along y direction. 2, 3, 4. So the first step what we have done, we have given first coordinates 1, 2, 3, 4. Next we have joined the coordinates 1, 2, 2, 3, 3, 4 and 4, 1. So to make lines. So when these lines are combined, so basically it has formed a closed surface, so which is called domain. So here it's a 2D structure, so we call it as a 2D domain. So once we have created the 2D domain, what we need to do next is to create the mesh. So how do we create mesh? By assigning the grid points along the edges. So we have taken along x-axis 4 grid points, and along y-axis also we have taken 4 grid points. Now, so what we do? So we join the grid points actually. So whatever the grid point number 1 we have along one boundary, same parallel grid point we have to join actually. So we have to join. We have to join. We have to join. So these are called the grid lines. So which are originated with the help of x grid point. Next, along y-axis we have to join this. Again, we have to join this. We have to join this. Let's say we have to join this. So what is the procedure we have seen? So we have assigned grid points and then we have joined those grid points which are parallel to each other, and which the x grid points has given the y lines and y grid points has given x lines. So basically these vertical lines are called y grid lines, and basically these x lines are called x grid lines. So the intersection of the x grid line and y grid line, so basically will give us the grid point, so which we have seen in figure 1. So this is the construction of the mesh, which is started from coordinates, next lines, next creating surface and the domain. Okay, so this is the procedure how we create a mesh. So simple 2D mesh. Fine. So now when we create the mesh, after that we need to give boundary conditions. So where we have given the names for BC1, BC2, BC3, BC4. So for each surface we will give the names. So that would be arbitrary. So it's of our own interest. So I have given BC1, next BC2, BC3, BC4. You can give B1, B2, B3, B4, or you can give, so this as a wall, this as outlet, and this as a top, and this is as left. So every user has its own interest to give it to give its boundary name. So it's your own interest. Now, so I have taken BC1, BC2, BC3 and BC4. So what name I have given? Bottom boundary, so which is nothing but the wall. I have given a boundary condition which is no slip wall boundary condition. And the right boundary, so the right side one, so I have given which is nothing but BC2, which is outlet, which is pressure outlet boundary condition. So on the BC3, which I call it as top. So for this I can give as symmetry, or I can give top wall or slip wall boundary condition. So let me give symmetry. Okay. So on the left side, which is nothing but BC4, I will give it as inlet, or you can give it as BC4. Now the boundary condition here it would be, so velocity inlet. Okay. So this will complete, what do you say, the meshing of the domain with boundary conditions with boundary names. Okay. So total how many number of grid points we have? We have 21. So here we have 21 grid points. Now, so the bottom one is wall, so which I have taken no slip. On the right side one we have a outlet, which is pressure outlet. On the top one we have symmetry, and the left side one we have velocity inlet. So given this boundary names and boundary condition, so we will import to solver actually. Now after solving we will get the results. When we get the results, so we will estimate what is the velocity at each and every grid point. So if, let us suppose at this location I am finding the velocity. So let me get, so we u at grid point, this particular location of I is 0.2 meter per second. Okay. So this is the velocity that has obtained from the solution. Okay. Now when we repeat the same process for another set of data in the sense, so here we have 21. So instead of 21, I will double it in the sense the 21 goes to 42. Okay. So when I change the number of grid points, and if the solution changes, again I will find the velocity at the same grid point when I changed the number of grid points from 21 to 42. Okay. So when it has changed to 42, if the result u of I is changing, let's say it has changed to 0.3 meter per second, then whatever the grid points you have taken was incorrect actually. So we have to change the number of grid points. So here again I will repeat it. Let's say, so I am doubling it. So 21 it has got to 42. The 42 thing it will become 84. Okay. So the 84, again I'll perform the simulation with the same boundary conditions and with the same boundary names. If the simulation results u of I again at the same location, if we are finding the velocity, so if it has come near to, let's say 0.25 meter per second, so it is reaching near convergence, so it is in between 0.3 and 0.2. Okay. And you have to again change the number of grid points. Now finally, let's say it's not finally, so we can change. If the simulation results are not changing, then you can stop here. If it is changing, you need to again perform the grid independency study. So which has gone to 168. Okay. So now when the simulation results are not changing, let's say it has come result of 0.24, let's say u of I, it has come 0.2499 meter per second or 0.2467, something like that. So it will not match exactly, but it may come near to the previous one. So let us take, this is the set of grid point 1, set of grid point 2, set of grid point 3, set of grid point 4. So we have 4 sets of grid points and the results, 4 sets of results, which is u of I of 1, u of I of 2, and u of I of 3, u of I of 4. So we have 4 sets of results. So when you compare these 4 sets of results, so what did you observe? So basically u1, u2, u3, u4. So basically u1, 2, 3, they are different. U3 and 4 are nearly equal. Nearly equal in the sense the error will be, let's say, less than 1% or let's say 0.5%, something like that. So if the error between the previous set of grid points and the current grid point is less than some value what we give 1% or let's say 5%, 4%, then we can conclude that this set of grid points will be eligible for performing the simulation. So this is what we call grid independency study. So I'll recall it again. So basically we will take one set of data which is X number of grid points. So when we take X number of grid points and when we double it or do it half, X in the sense, so let us take X as 21. So 2X in the sense, let us take this as 42. So when we change the number of grid points, if the simulation results change, when we take the number of grid points and when we change those number of grid points, if the simulation result changes, then whatever the grid points we take, those are inaccurate, and the simulation has to be continued till the convergence of the grid point has reached. Convergence of the grid point in the sense, as we change the number of grid points, if the simulation results does not change, we will take what is the lowest count of the grid points where the simulation results have reached the steady state. Okay, those will be the final set of the grid points for which we need to consider to perform the CFD simulations. Okay, so if you take the lower number of grid points, the simulation results will change and it will be not eligible for the simulation. Okay, so this is what we have for grid independence study. Now let's see what is time independence study and basically how do it impact for the CFD simulation. So there is a number called coherent number, CO, let us take. So which has come U delta T by delta X. Okay, so this coherent number, so basically this CO coherent number which is U into delta T by delta X, so is playing a major role in CFD simulation for stabilizing the numerical aspects. Okay, so we will see in detail what is the aspect of coherent number. Now let us consider again the 2D mesh. Let us consider again 2D mesh. Now what do we have actually? Let us take this as 0, 1, okay, 2, 3. So this is the name which I have given. Now the spacing between two grid points, so basically we call it as delta X, which is coming along X direction. Now spacing between two grid points along Y direction is called delta Y. So here we have delta X. So let's say this is delta X1, this is delta X2, this is delta X3, this is delta X4, delta Y1, delta Y2, delta Y3 and delta Y4. So delta X1, delta X2, 3, 4 we have. So if delta X1 equal to delta X2 equal to delta X3 equal to delta X4, then what is the meaning actually? So the spacing between two grid points at each and every section is equal. So this is called uniform mesh along x-axis. Now same you take along y direction, delta y1, delta y2, delta y3, delta y4. So what do we have actually? So delta y1 equal to delta y2 equal to delta y3 equal to delta y4. So if the delta y1, delta y2, delta y3, delta y4, if all are equal, then it has come that the spacing is uniform along y direction. Now if these things all are equal, so delta x1, x2, x3, x4 equal to delta y1, y2, y3, y4. So basically total set of grid, we call it as a uniform grid or uniform mesh. So when it is only along x-axis, we tell it as uniform mesh along x-axis and non-uniform mesh along y-axis. So basically what do we say is overall it is a non-uniform mesh. When we have both x and both along y, both along x and y, if the mesh points have this equal spacing, in general and in overall we call it as uniform mesh. Okay, now let us see the impact of the coherent number in this. So here basically if you see the structure of the mesh, so we call it as grid point, and so four grid points are constructing a cell, so which is a sub control volume or a subdomain of overall domain. So if you take the boundary 0, 1, 2, 3, so that is called a big cell or big control volume. So if you take the smallest unit in the mesh, so basically this is called the small control volume or the smallest unit, okay, which is formed by the combination of four grid points. Fine. Now, so when the CFD simulation process will go on, so what is the time taken by the fluid element to cross this cell, okay, so of the distance delta x. So that is the major contribution which is coming from the coherent number. So coherent number will give the information about what should be the time taken by the fluid particle to cross the cell. Okay, so the cell has delta x, delta y actually. So how much time it has taken. So let's say if the delta t is less than delta x, what happens? So by the time you see, the fluid particle will be inside the cell. Okay, and if delta x if is greater than delta t, so delta t is greater than delta x, what happens? Here the fluid particle will cross it. Okay. Now next we will see basically how the coherent number will impact all these areas. Okay, we have CO1, CO2, so here CO1 is there, CO2, CO3, CO4. So basically what is the meaning? Coherent number of first cell, coherent number of second cell, coherent number of third cell, coherent number of fourth cell. So likewise, so we have coherent number for other cells. Okay, so when we perform the numerical simulation, the coherent number will change with cell and in overall. Okay. So CO average, so CO AVG is nothing but of entire domain. CO of I in the sense this is of single cell. Okay. So here what is happening? Basically the coherent number changes with respect to the location. Okay. So why? Because the velocity at this location, it will be different actually. Okay. So if we, even though we have uniform spacing, but velocity will be different. That's why the coherent number changes. Fine. We are performing a simulation set of delta t. What is delta t actually? So time taken to perform the simulation from one set of data to other set of data. What is T1? So T1 is nothing but initial time. So what is T2? Final or the next Okay, so we have simulation, so where it is starting from 0 seconds. Okay, so the time bound between the initial and the final one. So what should be the minimum criteria? So that is very important. Why? Because it is relating to coherent number. Coherent number will give so information about the cell and the fluid that is crossing in the cell. Okay, so if you take too much small amount of delta t, what happens actually? The delta x also will go off. So the balance between delta t and delta x is very, very important actually. Now, so when we take delta x as, let's say, it has 0.1, and if the corresponding delta t should be matched such that the overall coherent number is coming less than 0.5. Okay, so the 0.5 is a condition or the criteria, so where the numerical scheme is stable actually. So here, in general, the coherent number is playing a major role to see the stability of a numerical scheme. So when we see the coherent number, so if the condition is, if it is less than 1, it is stable. If it is greater than 1, it is unstable. Okay, and depending upon the type of physics of the fluid you are solving, the coherent number changes actually. So for atmospheric boundary layer problems, ABL flows, the coherent number will be very large. Let's say it will be 10, 15, 20, 30. So it will be greater than 1. Okay. Now again I'm giving an important point. This coherent number actually changes with respect to the physics of the fluid. In general, you take the coherent number should be less than 1. If you take less than 0.5, it will be very, very stable. If you take nearly 1, it may oscillate actually. Okay. Now, what is time independent study? So, when we have delta t1, which is not equal to delta, let us take this delta t1 as, so this one as, so what is the meaning? Here delta t1 is 0.1 second, 0.2 second, 0.3 second. So when I change the delta t, so your numerical simulations should not change, your results should not change. So that is very, very important. Okay, so when it is changing in between t1, delta t1 and delta t2, so this will not be final actually. Okay, so if it is changing in between delta t2 and t3, this also will not be final. So these three are wrong. Now we have to optimize. What I have done, I have taken half of this. So I have reduced the time step. So when I am increasing the time step, the simulation is changing. So you have to do two process. One, increasing the time step. When it is increasing, if it is changing, you cannot do. So you cannot use that delta t. When you decrease the time step, if the simulation results are converging in the sense, if the results are getting steady state at lower time step, and when you take delta t and delta 1, if the results are nearly equal, you can consider delta 1. Okay, delta t1. Now even if these two, if they are not matching with each other, you have to go for another thing. So which is of, so I'm doing half. So I am halving it actually. So therefore, if the simulation results of these two are nearly equal or matching, okay, then we form a time independence study. So we get a time independence study. So what is the meaning actually? So when the numerical results are changing with respect to time step, you cannot use those time steps or delta t's. When the numerical simulation results are not changing, or let's say delta t4 and delta t5 we have, if the results for delta t4 and delta t5 they are nearly equal, we take delta t4 as our time step. So we will neglect this one and this one. Okay, so in the previously what we have seen delta we have seen set of grid points. Okay, so 21 grid points, 42 grid points, 84 grid points, 128 grid points. We have taken different sets of grid points. Now we are taking different sets of time steps. Okay, so this is the difference actually. Okay, now finally we will see basically what is convergence. So now the convergence is nothing but, so when we perform the CFD simulation results with set of grid points, let's say with set of delta t, okay, and with set of delta x, okay, with the set of grid points G. Okay, so we get the simulation results U of I. Okay, so next U of I plus 1. U of I plus 1 minus U of I. So basically, let us take I. I is nothing but 1, 2, 3, 4. You can take. So I plus 1 is nothing but the next step. Okay. So when the error between these two is, let's say, greater is 0.0001. Okay. So we will stop the simulation. Let's say it has come as 1 e minus 4. Okay. So our convergence criteria is 1e minus 6. Then simulation results will not change. So the meaning is the difference between the current and the previous, okay, values. If the value is less than 1 e minus 6, then you will stop the simulation. We say that convergence has reached. So we will take continuity, we take moment, x momentum, we take y momentum, we take z momentum, we take energy equation, or let's say we take temperature, we take, so let's say we have k, we have epsilon, we have omega. So we will give each and every variable the convergence criteria. So what we do, so we have all the things, k plus 1 and k of I, epsilon plus 1 minus epsilon I, omega of I plus 1 minus omega I. So for each and everything we give convergence criteria. So we say that if the error value or the difference between these two has come, less than this, okay, then we stop the simulation. If it is greater than that, we continue the simulation. Okay, so what we have seen actually, so we have seen the grid independency study, so we have seen the time independency study, and we have seen the conversion. So in the next lecture we will see how to actually perform a full form of simulation. So I will take an example of flow over flat plate. So we will perform a basic simulation using finite difference method or finite volume method, and we will sample run, we will see, and we will get a proper conclusion of the CFD simulation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.